In this question, we're asked to solve the following differential equation and to express our solution explicitly, which means in the form y equals, in this case, some function of x. And here our differential equation is a quantity x squared plus 1 dy dx equals xy. So first of all, we only know how to solve separable differential equations. So we need to start out by seeing if we can separate this expression. And by separate, what I mean is I want to get all of my y terms on typically the left side of the equation, and then all my x terms on the other side of the equation. So note I can also write this as x squared plus 1 y prime equals xy, where y prime is dy dx. So let's see if we can separate this. Well, I can divide the y over to the left-hand side and divide the x squared plus 1 over to the right. And if I do that, I can write this as 1 over y prime equals x over x squared plus 1. So this is separable. So I can solve it using the methods that we've learned for those kind of differential equations. So what do we do next in these situations? Well, what we do is we integrate both sides. In this case, we're going to integrate both sides with respect to x. So I get the integral of 1 over y prime, and I'm going to write this as y prime of x just for a second, dx equals the integral of x over x squared plus 1 dx. Okay, and then at this step you just have to remember a certain substitution, and that's going to be that y prime of x dx equals dy. So once I make that substitution, I can write this as 1 over y dy equals the integral of x over x squared plus 1 dx. Now at this point, my goal is to evaluate these integrals if possible. So let's start on the left-hand side with the simpler integral. I have 1 over y dy, the integral of that. Okay, so that's simply going to be the natural log of the absolute value of y. Okay, and then we can take a look at the right-hand side, which is perhaps slightly more complicated, but not too tricky. Over here, we just need to do a simple u substitution. Let u equal x squared plus 1. So du is 2x dx, or 1 over 2 du equals x dx. So then this integral becomes the integral of 1/2, and then I have a 1 over u du. It's going to give me 1/2 natural log of the absolute value of u plus some constant of integration. And if I substitute my original expression back in, 1/2 natural log of the absolute value of x squared plus 1 plus my constant of integration. Okay, so then what I have is I have the natural log of the absolute value of y equals the natural log of the absolute value, or sorry, there should be a 1/2 there, equals 1/2 natural log of the absolute value of x squared plus 1 plus my constant of integration. Now, you only need to include a constant of integration on one side of your equation. So I only need this c1 on one side. Now, we're not given any initial conditions in this case, so our solution is going to be what we call a general solution. So in the end, I am going to have some constant of integration in my final answer. So what should we do next? Well, remember the instructions say that we need to express our solution explicitly. That means that I need to solve this equation for y. So let's try to do that. I need to get rid of this natural log, right, if I want to isolate y. So the way in general that I cancel out a natural log is by using an e, its inverse. So I'm going to use a base of e on both sides. So then on the left-hand side, this is just going to become the absolute value of y. And then on the right-hand side, I have e to the 1/2 natural log, and I can go ahead and drop these absolute value symbols because x squared plus 1 is always positive anyway. So I have this whole expression in the power of the e. Okay, so let's keep simplifying here. I notice on the right-hand side I have e to the 1/2 natural log of x squared plus 1. Okay, so that looks like, and then plus c1. So I do have an e and a natural log, but it's not quite at the point where I can cancel those out yet. So let's try to do a little bit of rearranging up there. Okay, so first thing I can do is I can split up this sum. Right, I've got 1/2 natural log of x squared plus 1 plus c1 in my exponent. I can split that up into two different expressions. So in other words, e to the 1/2 natural log of x squared plus 1 times e to the c1. The rules of exponents allow me to split up the sum in that way. Now further, in that first factor there, I can write this as e. So I've got this coefficient of 1/2 in front of the natural log. I can make that a power within the natural log and write this as e natural log of the square root of x squared plus 1. And then I still have this e to the c1 power. Okay, so now I can cancel out this e in natural log. So I have absolute value of y equals, I'm going to write this as e to the c1 times the square root of x squared plus 1. Now I still haven't quite isolated y. I've got the absolute value of y. But if I wanted to write this as y equals something, remember that the absolute value, of course, takes something that is either positive or negative and makes it positive. So if I kind of want to undo that absolute value, what that's going to look like is using a plus or minus here. So I can write this as y equals plus or minus e to the c1 square root of x squared plus 1. Right, because then the absolute value of y would just be this positive expression that we have up here if we took the absolute value. All right, there's only one last step. I have this plus or minus e to the c1, and c1 represents just some arbitrary constant. But e to the c1 is also an arbitrary constant, and plus or minus e to the c1 is also just an arbitrary unknown constant. So I don't need to write plus or minus e to the c1. I can just rename this to be c, just for easier notation. So then this becomes y equals c square root of x squared plus 1. And this is an explicit solution, right? I have y as a function of x. Now it's always a good idea to, if you have time, to just check and see if your solution actually satisfies the original differential equation. So let me just show how you would do that really quickly. So if I glance back up here on my original differential equation, so we're just going to check really quick. I had x squared plus 1 dy dx equals xy. So I guess I need to find dy dx. Okay, so dy dx then, let's see, well I'm going to keep this c out front, and then I have x squared plus 1 raised to the 1/2. So that's going to be times 1/2 x squared plus 1 to the negative 1/2 times 2x. Okay, so if I simplify that, I get the following. Cx over the square root of x squared plus 1, right, because my factors of 2 cancel out. Okay, and so if I just started plugging in here to the differential equation, I have x squared plus 1 times dy dx, which I just found to be cx over the square root of x squared plus 1. And that should hopefully equal x times y, which y was c times the square root of x squared plus 1. Okay, so let's do some rearranging. Well, I've got a c on both sides, so I can cancel those out right off the bat. And then I can multiply my, multiply my square root of x plus 1 to the other side. So that I have x squared plus 1, x equals x times square root of x plus 1 times square root of x, square root of x squared plus 1 times square root of x squared plus 1. These x's cancel, and I can see from here that this is going to work, right? That this is a true statement. So we have actually found the solution. In this problem, we're instructed to solve the following initial value problem and to express our solution explicitly. And we have y prime equals y cubed e to the negative x, and then the initial condition y of 0 equals 7. So the fact that we're provided with initial condition here means that we should be able to solve for our constants of integration. We shouldn't see any c's in our final answer. Okay, so our first step is going to be to separate this differential equation, if we can, which in this case we can do that. So if I separate it with the y's on the left, x is on the right, I'm going to get 1 over y cubed, y prime equals e to the negative x. Now from here, I want to integrate both sides with respect to x in this case. So I get 1 over y cubed, y prime dx equals the integral of e to the negative x dx, but y prime dx is just dy. Okay, so this becomes, I'm going to write this as y to the negative 3 dy, the integral of that, equals the integral of e to the negative x dx. So then my next step is to evaluate these integrals if possible. Okay, and these both look pretty straightforward. So on the left-hand side, I'm going to get y to the negative 2 over negative 2. And then on the right, so equals, the integral of e to the negative x is negative e to the negative x, and then I have plus a constant of integration. Okay, so let's go ahead and clean this up a little bit. We can start by multiplying both sides by negative 2, so that this becomes y to the negative 2 equals 2e to the negative x minus 2c1. Remember ultimately that I'm going to want to solve for y. All right, so that's why I want to clean this up a little bit at this point. So I have y to the negative 2. If I want to make that a y squared, right, so really what I have here on the left is 1 over y squared equals 2e to the negative x minus 2c1. Okay, so then if I wanted to, instead of 1 over y squared, have just y squared equals, I would have y squared equals 1 over 2e to the negative x minus 2c1. Now 2c1 is just an arbitrary constant, just like c1 was. So for simplicity, I am going to rename 2c1 as c. Okay, so then what I end up with is y squared equals 1 over 2e to the negative x minus c. Now, I do want to solve for y ultimately, but if I want to, I can actually go ahead and solve for c right now. It doesn't really matter when I do it, but sometimes it might be a little easier to solve for c when you're still in this implicit form. So let's go ahead and find c. So to find c, I need to use my initial condition, which was y of 0 equals 7. Okay, so I'm plugging in 0 for x and 7 for y. So I get 7 squared equals 1 over 2e to the 0 minus c. Okay, so this is 49 equals 1 over 2 minus c. Right, so I can write this as 49 times 2 minus c equals 1. 49 times 2 is 98, so I get 98 minus 49c equals 1. So this becomes 97 equals 49c, or c equals 97 over 49. So if I substitute that back into our implicit solution up here, we get y squared is 1 over 2e to the negative x minus 97 over 49. Now to finish out this problem, we need to solve for y, since we're asked to express our solution explicitly. Okay, so to solve for y then, I am going to take the square root of both sides. So I get y equals plus or minus the square root of this expression, 1 over 2e to the negative x minus 97 over 49. Or I can write that as y equals 1 over plus or minus the square root of 2e to the negative x minus 97 over 49. Okay, so we're still not quite done yet. There's two issues here, really. One issue, first of all, is this isn't actually a function of x. If you were to graph this, it would not be the graph of a function. It wouldn't pass the vertical line test. So that's one issue. It's not an explicit function. The other issue is that when you take the square root, or have cases like this, and you end up with this plus or minus, it's not necessarily true that both the plus and minus are going to be actual solutions of the differential equation. So what we need to do is we need to check this plus or minus thing and see which of those are actual solutions. And to do that, we're just going to use our initial condition again. Well, I want my solution to pass through y of 0 equals 7. And 7 is positive, right? 7 is a positive number. So I want then the solution to be positive. So I want my solution to be positive for x equals 0. Okay. Now this solution here, this 1 over plus or minus the square root of such and such, is either going to be always positive or always negative, right? Because the output of the square root function is going to be positive. So then what I want to do is I want to choose the positive root. Because if I choose the negative root, then this function is going to be negative always, and particularly for x equals 0, so then it wouldn't satisfy our initial condition. Okay, so then as my final answer, I'm just going to choose a positive root. So 1 over the square root of 2e to the negative x minus 97 over 49. And this now is an explicit solution. In this problem, we're told to solve the following initial value problem to leave our answer in implicit form. We have y prime of t equals y squared plus 16 over t squared plus 4, and the initial condition y of 2 equals 4. So we want to start by seeing if we can separate this differential equation, and I can. If I separate this, on the left-hand side, I get 1 over y squared plus 16, y prime, and then on the right, 1 over t squared plus 4. So then I can proceed to integrate both sides of the equation, in this case with respect to t. So I get this expression. Okay, and then I just note that y prime of dt equals dy. So I can write the integral of 1 over y squared plus 16 dy equals the integral of 1 over t squared plus 4 dt. And now I'm ready to integrate. So in this problem, there is a particular integral formula that I need to recall, and that is the following. The integral of 1 over x squared plus a squared dx equals 1 over a inverse tangent of x over a. And that's the situation I have for actually both of my integrals here, which is nice. So on the left-hand side, if I try to kind of match it up with this form over here, I've got y squared plus 16, so my a value is 4, right? 4 squared equals 16. So on the left then, this is going to be 1 over 4 inverse tan of y over 4. And then on the left, I've got 1 over t squared plus 4, so here my a value is 2, so I have 1/2 inverse tangent of t over 2 plus some constant of integration, which I will call c1. Okay, so in this case, I am allowed to leave my answer in implicit form, so I'm not going to have to solve for y, which is really nice, because here I have some pretty complicated functions. But I do need to solve for c1 because I am given an initial condition. So the initial condition I'm given is that y of 2 equals 4. Okay, so when t is 2, y is 4. So let's plug in those values. So I'll plug in 4 for y and 2 for t, and I have this expression here. So this becomes 1/4 inverse tan of 1 equals 1/2 inverse tan of 1 plus c1. Then we have to remember what the inverse tangent of 1 is. We can ask ourselves, where is the tangent equal to 1? Though you also have to recall that the inverse tangent has a limited range. But anyway, the inverse tangent of 1 should be pi over 4. So I have 1/4 times pi over 4 equals 1/2 times pi over 4 plus c1. Okay, so it looks like I get pi over 16 minus pi over 8 equals c1. Well, I could write that as pi over 16 minus 2 pi over 16 equals c1. So it looks like c1 is negative pi over 16. So from there, we can substitute that value back in to our solution and get 1/4 inverse tangent of y over 4 equals 1/2 inverse tangent of t over 2 minus pi over 16. And we can just leave our answer like this since we are looking for an implicit solution.